Hi everyone, I am Yogesh, a PhD student at the University of Illinois Urbana-Champaign, and today I'm here to present our work, which is about a flexible EDA sensor made up of silver nanoparticles for EDA sensing. So if we look into construction, then construction workers, there is like high demand in their roles, the tight deadlines, and challenging environmental condition, because of which mental stress is a very big problem in construction for construction workers. As a matter of fact, compared to similar occupation like in manufacturing or mining, construction workers have one of the highest rates of mental stress. So this significantly affects in worksite safety and productivity. Uh, so if we look into existing method for mental stress or cognitive load or uh, stress monitoring, then most of the methods are based on questionnaires and surveys like the NASA TLX. So the problem with these methods is they cannot be continuous, they are intrusive. You cannot be asking like when construction workers are working in the field, are you feeling stressed out or not, because it's a continuous way. So also they have limitations of they are subjective in nature, they have biases. So to say in like one word, so this kind of methods cannot be used in field for the actual monitoring applications. So this is where EDA comes in play. So EDA sensor, they capture the electrical conductance of skin, which fluctuates with sweat gland activity. So this is a part of sympathetic nervous system, and we have seen studies that have been able to interpret the EDA signals to cognitive load and mental stress using mathematical models or machine learning models. So if we look into the existing solutions for capturing the electrodermal activity signals, then most of them are for clinical settings where you go into an hospital, you are seated, and then they are able to capture the EDA signal in a good way. But when you are moving, when you are working in the field, then there are a lot of problems. The common ones are like IFO empatica. It's like IFO empatica Fitbit Sense, which is a wristband based method. So if you are sitting, if you are relaxing, then they have a really good performance. But when you start to move, then there is a lot of motion artifact, and it may not be able to acquire signals with good amount of signal to noise ratio. So there are other like AD instruments. These are more based on lab, where you wanna like capture signals in the rest position. Uh, so like basically these challenges can be categorized into two forms. So one is the non-flexible design. When we look into the previous one, like most of them are rigid. So if you are seated, if you are in rest, it works good. But when you are moving, then it does not conform well with the skin. um, and well, they are designed for clinical settings, and because of this there's a lot of motion artifact, low signal to noise ratio, because of which if we are to use this in other application like some monitoring application, then there is a reduction in performance. So to summarize, existing sensors are designed for controlled environment and lab settings and clinical settings, because of which when someone is trying to work in the field, it can have poor skin contact, high contact impedance, and that can compromise the signal quality. Therefore, the objective of this study was to design and develop a flexible EDA sensor which can conform with the uh, texture of skin, and so it can provide good signal to noise ratio when we are operating it in dynamic construction environment. So basically, first we started by modeling some fractal curves, and then we fabricated it using direct ink writing based methods, and then we analyzed it doing some construction tasks. So the first step was so based on the previous literature, we um, like got some of the fractal curves. So these are like repetitive geometries that are present in nature, which have like highly conforming geometries. So because of that, it has a good flexibility as well as it covers a good amount of area. So we took around 8 curves for this. So these are all based on literature. Then we model it. Then for like initially before we fabricated it, we did some stress strain test using like extension and some fatigue analysis. So this is only static loading. So for that we used an extension force of around 1 to 2 Newton, which is like a typical force for extension of skin in normal work environment. Uh, and then after this, like so when we and I'll show you the results later, but based on this, it's like the first row, second column, Peano-Gosper 3 had the best results. So we went forward by fabricating it. So for the substrate, we used polyamide substrate because like it has good flexibility, which is close to that of the skin, and it has it has good thermal conductivity, as well as it does not expand much. So this is good for our applications, and it is also used for other kind of flexible sensors for humans. And then for the ink, we used silver nano inks because silver has a very good conductivity. And then we used a piezo module based printing mechanism. So there is a polyamide substrate, and the silver ink is printed on it, and then we have a clinical adhesive which can be then used in the human skin. After it's printed, we use some UV pulse sintering so that the AZNP, like the silver nanoparticles, can be so the solvent in that ink gets uh, evaporated, and also it gets stabilized. So in this experiment, the main purpose was to see reduction in signal to noise ratio. So for this, we chose hammering tasks where the subject wore the developed electrode in the fingers, and then the subject was asked to hammer nails into the singles in a roof structure. So there's a lot of motion while they are doing this tasks. And for signal acquisition, we use AD instruments. So we had 12 subjects, and so for out of the developed, so we have two results. So in terms of single signal to noise ratio, in that static position, we were able to have around 8 decibel of improvement, which is significant. And when the subjects were at rest, the performance is similar because the commercial sensors do really work well when you are in seated position when you are resting. So yes, the developed sensor did provide a significant improvement when we were in motion. And then these are just the stress and strain results for the initial finite element analysis that we did for the various corps that we studied. So the research finding highlighted the potential of silver nanoparticle modified flexible sensors for reliable signal acquisition, as we saw a significant improvement in SNR. So it has the potential to be used in mental stress and cognitive load monitoring. So the future step would be to integrate this developed sensor into the real-time like machine learning models and electronics or mobile application to deploy it in the field in real time. So in the end, I would like to thank my colleagues from Raise Lab and our funding agencies. Thank you everyone.